we are going to see how to derive Maxwell's equations from mnemonic diagram. This is a mnemonic diagram, so we'll go into the details of the diagram later. So before that, we'll see the steps involved in deriving Maxwell's equation from mnemonic diagram. The first step is to write down total differentials from the diagram, and from the total differentials, applying exact differential rule, we'll be able to find out Maxwell's equations. So you can see here, so this is a sample total differential. From this differential, when we apply exact differential rule, we will be able to arrive at Maxwell's relations or equations. To understand how to write down the total differentials from the mnemonic diagram, we need to first understand the mnemonic diagram. So in the mnemonic diagram, the sides are labeled with four common thermodynamic potential, that is internal energy, Helmholtz free energy, Gibbs free energy, and enthalpy. They are labeled in clockwise direction. We can see from the diagram that it is in alphabetical order, that is A, G, H and U. So A is at the top of the diagram. So the corners are labeled with extensive parameters, that is volume and entropy, the extensive parameters on the left side corners, and in the right corners we can see temperature and pressure, which are the intensive thermodynamic parameters. The energy properties are flanked with their canonical or natural variables. Internal energy is flanked with its own canonical variables, that is the total differential variables, volume and entropy. Helmholtz free energy flanked with volume and temperature, which are its natural canonical variables, that is the total differential variables. And Gibbs free energy is flanked with temperature and pressure, and enthalpy is flanked with entropy and pressure, which are its natural canonical variable or total differential variables. So the first step is we'll be writing canonical variables. The second step is going to be identifying the coefficients. Each canonical variable will have a coefficient, and these coefficients will be found out using these diagonals given here. So you can see the diagonals here. So these diagonals will be used to identify the coefficients. So the second step is identifying the coefficients. The third step is to assign sign convention. The sign convention will be based on the diagonal arrow's direction. For example, if the arrow is pointing away from the coefficient, then we will be giving negative sign, and if the arrow is pointing towards the coefficient, we will be giving positive sign or plus sign. So we can see, if for example, if temperature is a coefficient, so the diagonal arrow is pointing towards temperature. So because of that, so we can assign positive sign. Similarly, if we take entropy on this side, the arrow is pointing away from the entropy, so we'll be giving negative sign. Let's see how to write the total differential for internal energy. So let's start by writing the equation. So the equation will not be mathematically sensible until it is complete. So for the purpose of constructing the equation, I'll be writing certain steps. So to start with, so we'll write du. We'll identify the canonical variables of the internal energy. So the canonical variables are flanked. So you can see the canonical variables V and S. So what I'm going to do is I'm going to write the canonical variables in their differentials. So it is going to be ds and dv. And the next step is to write the coefficients that are diagonally opposite to the canonical variables. So we can see opposite to volume we have pressure, and opposite to the canonical variable entropy we have temperature. So we are going to write down those coefficients. So we'll continue with the equation. So for entropy we can write temperature, so that is T dot Ts, and for volume it is P, so I'm going to write P dot dV. Now comes the sign convention. So let's see the direction of the arrow. So if the arrow is pointing towards the coefficient, then the sign must be plus. If it is away from the coefficient, so the sign must be negative. When we take the coefficient temperature, the diagonal arrow is pointing towards the temperature, so it is going to be plus for T. And when we take the coefficient pressure, so the arrow is pointing away from pressure, so we are going to give a negative sign. So this is the total differential for internal energy, which is du is equal to TdS minus PdV. Let's write down the total differential for enthalpy using the mnemonic diagram. So we can see from the diagram, so enthalpy is flanked with entropy and pressure. So we'll start writing the equation. So that is dH is equal to ds and dP. So now it is the time to identify the coefficients that are diagonally opposite. So we can see for entropy, temperature is the coefficient, and for pressure, volume is the coefficient. And for both the coefficients, the diagonal arrow is pointing towards them. So both of them can be given with plus sign. So we can write the equation as T dot ds plus V dot dP. So this is the total differential for enthalpy, that is dH is equal to TdS plus VdP. Now let's write down the total differential for Helmholtz free energy A. So we can see A is right here. So Helmholtz free energy is flanked with its natural variables volume and temperature on either sides. Now let's write the equation. So we can write it as dA is equal to the canonical variables dt and dV. So to identify the coefficient, so we can look at the corners that are diagonally opposite. So for temperature, the coefficient is entropy, and for volume, the coefficient is pressure. And as we can see here, the diagonal arrow is pointing away from both the coefficients. So because of that, we can give them both a negative sign. So we can write it down. So minus SDT minus PdV. So the total differential for Helmholtz free energy is dA is equal to minus SDT minus PdV. Similarly, we can write for Gibbs free energy G, so which is flanked with its canonical variables T and P. So let's start writing the equation. dG is equal to the canonical variables, that is dt and dP. So now let's look at the coefficients. Okay, so you can see the coefficients that are diagonally opposite. So the coefficient for pressure is volume and the coefficient for temperature is entropy. And we can see the diagonal arrow is pointing away from entropy. So we can write it as minus S dt, and the diagonal arrow is pointing towards volume. So we can write plus V dP. So the total differential for Gibbs free energy is dG is equal to minus S dt plus V dP. So now we have all the four differential equations. We will see how to write Maxwell's equation from the total differential expressions. The total differentials for all the four thermodynamic potentials are in the form dx is equal to m dx plus n dy. When we apply exact differential rule, so the total differential can become dou m by dou y when x is constant, and this is going to be equal to dou n divided by dou x, where y is a constant. So this is how a Maxwell equation will look like, and we can get the Maxwell's thermodynamic relations for all the four potentials using the same exact differential rule. The Maxwell's equations for all the four potentials are tabulated here along with their total differentials and their canonical variables. For internal energy, the canonical variables are entropy and volume, and the total differential is du is equal to TdS minus PdV. The Maxwell's equation goes like this: small change in temperature with respect to small change in volume at constant entropy is equal to minus small change in pressure by small change in entropy at constant volume. Similarly, for enthalpy, whose canonical variables are entropy and pressure, the total differential is dH is equal to TdS plus VdP, and the Maxwell equation goes like this, that is small change in T by small variation in pressure at constant entropy is same as small change in volume to the slight variation in entropy at constant pressure. And for Helmholtz free energy, whose canonical variables are temperature and volume, the total differential is dA is equal to minus P dV minus S dt. The Maxwell's equation for Helmholtz free energy goes like this, that is a small change in pressure to the small change in temperature at constant volume is same as small change in entropy by small change in volume at constant temperature. And for Gibbs free energy, whose canonical variables are temperature and pressure, the total differential is dG is equal to VdP minus SdT. Maxwell's equation for Gibbs free energy goes like this: a slight variation in volume with respect to a slight variation in temperature at constant pressure is equal to negative or minus slight variation in entropy with respect to light variation in pressure at constant temperature. So these are the thermodynamic potentials, their total differentials, and their Maxwell's equations, which can be easily written from mnemonic diagram.